Peregrine Falcon, Dynamics and Control by Max and Alex. Falco peregrinus, more commonly known as the peregrine falcon, is one of the world's premier aerial hunters. They prefer to hunt in wide open spaces, thrive near coasts where there is plenty of prey, and have more recently been found to live and hunt from skyscrapers and bridges in major cities. These falcons hunt other birds and small land-dwelling mammals, doing so by diving on them midair. Peregrine falcons have a length of 34 to 58 centimeters tip to tail. They have a weight of about 0.53 to 1.6 kilograms, a cruising velocity of 15 to 30 meters per second, and a top speed of 108.2 meters per second, which is an astounding 242 miles per hour. While diving, these falcons carry an average of 9 kilojoules of kinetic energy. They also feature notched upper beak for severing their prey's spinal cords, razor-sharp talons, and a perfect aerodynamic body shape.
Dynamics of falcon flight. Peregrine falcon flight is governed, as with all systems, of Newton's second law of motion, F equals ma. Based on the frequency at which they beat their wings and the amplitude of their wing stroke, they generate enough lift to counteract their weight to maintain steady flight. This dynamic process is continuous because the falcon constantly takes in the sight of its surroundings in order to maintain the appropriate trajectory control. In addition, the falcon uses proportional navigation, similar to a modern missile, by making slight adjustments in wing position and the speed before catching its prey. Control of falcon flight. In flight, the peregrine falcon visually navigates itself based on optic flow. Optic flow is the apparent angular velocity of the surface with respect to the falcon when moving through passages. The falcons maintain equal distance between trees by trying to balance the apparent angular velocities of the surfaces. Falcons take in the sight of its surroundings and use it to determine the optic flow of the surface it's between. Error between these apparent angular velocities in conjunction with previous flight path is then used to determine the new flight trajectory. This is why it is a PI control system. In the diagram, we can see this is a schematic block diagram of the system where the input is the sight and the eyes, and then the optical control function is the second block. Third block is the PI controller, which is the brain, and then in between that is the air between the optical control, and lastly the output is the flight path trajectory. In an experiment done by researchers, birds were trained to fly along a corridor where the walls were lined with stripes that were oriented horizontally or vertically as seen in figures A, B, and C. The birds' flight trajectory were recorded in 3 dimensions by a pair of high-speed stereo video cameras operating at a frame rate of 250 frames per second, and then reconstructed using custom-written MATLAB software. In figure A, when the 2 walls were lined with vertical stripes, the birds flew along the middle of the corridor, never colliding with either wall. In this situation, both walls induced strong image motion in each eye because the stripes were oriented perpendicularly to the direction of the flight. On the other hand, when one wall was decorated with vertical stripes and the other with horizontal stripes, the birds flew significantly closer to the wall carrying the horizontal stripes as seen in figures B and C. These results reveal that the birds travel through narrow passages safely by steering a course such that the 2 eyes experience similar rates of image motion or optic flow. When both walls carry visual textures that provide optic flow, as seen in cases in natural environment, this strategy ensures that the birds fly a collision-free path along the middle of the passage.
While hunting, peregrine falcons coast at a high altitude steady state while searching for prey. In this part of the hunt, their body frame is relatively stable with respect to the Earth-centered inertial frame. Once they have located their prey, they tuck their wings and rapidly change their relative angular velocity, converting their potential energy into kinetic energy. Once tucked, their body frame stabilizes again to the inertial frame as they collect as much speed as they can. Once they are sufficiently close to their target and have enough speed, they unfurl their wings, regain control while while retaining an immense amount of speed and latch onto their prey, effectively completing the attack. So let's watch now as a peregrine falcon attacks a pelican, a bird 4 times its size. Notice how it uses its wings to stabilize its body frame with respect to the pelican's body frame, and then uses its talons to attack it once they're aligned. The peregrine falcon is truly an example of a perfect yet deadly controlled aerodynamic system.